You're on.
Okay. So basically today what we're gonna do is last time we did can you tile squares with polyominoes? Which was kind of like a test for how this rough format is gonna go. And this time it's gonna be a similar format where I will pose questions without specific answers, and you're gonna try to see if you can solve them. Our problem here is, can every polyomino be folded into a rectangle with some thickness? Be folded into a rectangle with some given thickness. Yeah. So here's an example. I'm gonna take like a, I don't know, we're gonna take like a p pentomino. And then we're gonna fold it such that, let's say, the creases go like, okay, the creases go like here once and here once, right? And then what you eventually end up having is this new shape, which is this rectangle here, such that the two layers, the layers fold onto each other, and the new rectangle has a uniform thickness of 2. So the thickness here would be 2. So this satisfies that I have a rectangle and it has some thickness. So our problem in general is, for each polyomino, let's say for the polyomino, this is keep flashing.
Thickness has to be uniform. It can't be like bounded. Like
Yeah, it has to be.
Okay.
Yeah, it has to be uniform. As in, you can't have part of it that's one thickness and part of
Gotcha.
it that's another thickness. Right? So in general, our problem would be, given like a random polyomino, let's say this polyomino, is it possible to make this into a rectangle of, right? And it's any rectangle, right? The folds do not necessarily have to like be on the grid line. So like here, any rectangle of some thickness, let's say, I don't know, 6, right? Is it possible or is it not possible? Or like, let's say 67,
Well, in that
right?
case, well, 6 is easy. You just fold the whole thing up, right? Each square, you just fold it down into a single square by following the grid
Right.
lines.
We're gonna see that these are, in general, easy. And I have a rough heuristic argument. This talk is gonna have a lot more open problems. Oh, well, I guess not a lot more, but some more open problems than the previous talk. Mainly because this is like a new, like novel kind of problem. We're gonna start with okay, so the way that this is gonna work is that we're gonna analyze every single polyomino, and then we look at what thicknesses such that the rectangle would fold. So for instance, let's start with the simplest of the polyominoes, one by one. Uh, Anybody has any idea at what rectangles it can be folded into? But like, like what thicknesses that the rectangle can be if it's uniform thickness?
Any integer, any positive integer would work.
Yeah, any positive integer. So I'll denote this as 1 all the way to infinity. Even though it's like an interval, I'm only selecting the positive integers. So you can assume that I'm intersecting this with positive integers. Right. Yes, thickness is exactly n. Yeah, and this would be possible for any n. And in general, any rectangle would be possible for any n. So we've also done the case for domino. And the logic behind it is, if you have some n, let's say 3, then you just fold it like into thirds, and then this will just come into a zigzag shape such that the thickness is always 3. So that is easy. Now that we've done the monominos and dominoes, let's look at the trominos. Obvious trivial one is again the 1 by 3, which again is all positive integers. But now let's look at this L shape, right? This L tromino. Guesses for what thicknesses the L tromino can be? can be folded into?
Well, at least you can definitely accomplish all 3n by just folding it into a square first, and that seems like it generalizes like um, n times m, where m is the number of boxes in your m omino, I guess. Then you can always construct nm just by folding it up into
Okay,
a square.
right. So obviously we have 3 times natural numbers, and in general, yeah, this is true. And the reason is because for any rectangle, I already know that if I have a rectangle, then I can get it to any thickness. And in general, this is like reduction. So for instance, um one of the problems in origami puzzles is like this, right? It's like asking, and this isn't a polyomino, but this also works. This is like, can you fold this into thickness 4, which I'll notate with T4? And the solution is you first fold it like this, which means that you now have like this kind of shape, which is like a 4 by 4 with a 2 hole. And then it turns out that you can fold this into thickness 2, with an interesting set of folds that I'll not go into. Um, so this is, if you can reduce it into some uniform thickness shape, and then that can be reduced into uniform thickness rectangle, then you can just multiply the thicknesses together to get the result. So 3n is also possible. Right. But also all multiples of 2n. Reason?
Because you can fold the half of one corner and then fold the entirety of the other corner, and the result becomes 1 times 1.5 rectangle.
1 times 1.5. Oh, yeah. Okay. So you could. Right. Okay. Let me draw that out. So, yeah. One thing you can do. I should just learn how the short key works. Actually, um, that's gonna be a time save in the long run. Okay, I see. So in general, so here you can do this, folding it into a 1 by 1.5, and that's a thickness 2. So you can also do like on any multiple of thickness 2. Great.
Are folds which are not orthogonally aligned allowed? Can we do like diagonal folds?
Yes.
Okay.
Yeah, and specifically this one, as Tusop, yeah, as Tusop says, this is done with the operation in which like you do diagonal folds like this, and this resolves it into a rectangle, which looks like,
You can
which is the rectangle here.
wait. You can.
So,
I mean, you can
so
do it
just
without
to,
relying on that. You can just like fold the top half and then the bottom half in. Oh wait, can you not?
There's a hole in the middle, so
Oh crap!
that
I'm
wouldn't be.
thinking. Yeah, but you would then no, but then you would fold the outer two sides. You would fold it into the. You'd fold the whole shape into the donut hole, basically. You fold the top down and the
Then it
bottom
would be,
up.
then it would be thickness 3. If
Is
I
that not
understand.
what we're going for? Are we trying to do two?
Yeah, like the example I was giving is that like this is solvable with thickness 4 because you can reduce it
Oh, okay.
thickness 2,
I see.
and then this can be solved thickness 2.
Gotcha.
But if this were thickness 6, then your solution would work because it would be thickness 2 into this, and then this would be solved thickness 3 with your method. Okay.
just to clarify really quickly, we're saying that we can do the diagonal folds as long as we end on a uniform rectangle.
Yeah, we can do any folds, and by any fold, we'll assume straight line folds.
Okay,
We can do like any folds, not necessarily aligned to the grid lines and not necessarily orthogonal, and it's as long as we end up with a rectangle with
got
a
it.
certain. Yeah. Anyways, um, we've proved that this is solvable for 3n and this is solvable for 2n, right? I mean, it's clearly not solvable for 1 because this isn't a rectangle and any fold will introduce thickness. I hope that's a sufficient argument. And so 1 is done, 2 is done, 3 is done, 4 is done. What about 5?
Intuitively, 5 is a prime number, so it couldn't be made out of rectangles, shouldn't it?
Yeah. Oh, hi, Zach. I would definitely be okay with it. I'm not sure how it would work on recording. I think it works. Based on what I know about how the recording works.
I'll just switch between screens when it looks appropriate. Go for it.
Okay. Okay. I will also need to watch though, so that means I'll have to look at. I guess I can do it on phone. It's fine. Okay. But anyways, this triangle is
5 being prime doesn't disclude it immediately. Like we can do 3, but 3 is prime. I mean, the problem is that it's not yet divisible by something that we already know how to do, but I don't know the.
I'm gonna do a super big spoiler, which is that proving that something is impossible is like really, really hard. I'm just gonna say impossibility is hard. And specifically, I haven't been able to prove any impossibility other than trivial cases, as in like think this equals 1. Now, that does not mean that necessarily 5 is possible. It might be that I don't know, and I'm just trying to, I don't know, alien conspiracy. But
Wait, sorry. Are you saying this is an open problem?
I'm giving y'all time to work on it.
Oh, okay, but the
I'm
answer's
gonna.
no.
Yeah, I'm okay. The result is that 5 is possible, and it is via the following. It is via the following. So first, we start with this tromino, and then what we can do is we do this fold. So this folds it upwards, and what I get is something I can notate with a 2-1, or basically the left square has a thickness of 2, and the right square has a thickness of 1. What I can do now is that I can recognize that 5 is equal to 2 plus 2 plus 1. And it's also equal to 1 plus 1 plus 1 plus 1 plus 1, which means that what I can do is I can fold the 2 in half. So I can get a 4 and a 1. And then I can fold the 1 over. And this means that I'm left with a single square where 1 is on the left and 5 is on the right. And now the one rectangle can be zigzagged 5 times, such that folded 4 times, but 5 into 5 equal parts, and the result will be a thickness of 5. Does that make sense? And I'm gonna give y'all a few.
That's quite cool. I think you flipped the 1 and the 5 though, didn't you? The 5 should be on the left and the.
Okay. Like the way I drew this, I intended for like the 2 to be folded in half and the 1 to be folded the other way. But so if you fold the 2 in and then in again, that would be like the other way. It doesn't matter, basically.
Okay. Yeah. I'm with you.
Okay. There is a similar result, therefore, related result or corollary. If I have a scenario where I have an n and then 1, what I can do is I can let me think about how I want to portray it. For all numbers that is greater than a certain threshold, I can construct it. Like I can find the relevant thickness. And the threshold, I believe, is something like n times n minus 1, but I'm not sure. I'll need to adjust it slightly. The rationale behind this is you can like if we have a thickness that is equal to an plus b, then what I can do is I can fold this n into 8 bits, like I can fold this n into a parts, so I get a tiny strip which has a thickness of an, and then a bit of 1. I can fold the 1 over b times, so I eventually end up with an plus b and then a 1. And this is going to be an plus b. This is going to be 1. So I fold the 1 5 b times. It might end on either side, but it doesn't matter. And this allows us to make it happen. This allows it to work.
But
Um,
this would only work if B is less than A.
yeah, this would only work if b is less than or equal to. I'm not completely. Again, I'm not completely sure about the boundary condition. Let me look over this.
Like, I don't think that's an actual problem because, like, you know, at that point you could just rewrite A as being one greater. But
Yeah. Okay.
yeah,
That's why I wanted to go back to the threshold, because I didn't calculate this in advance, but I have the rough argument that it works. Okay, so yeah, if b is greater than a, then you don't have enough to cover it b times. Therefore, b is less than or equal to a. If a is equal to, well, when a is at least n, that's not a problem. In fact, b can at most be n minus 1. So if a is n minus 1, then it doesn't matter what b is, it always works. But if a equals n minus 2 and b equals n minus 1, we can't guarantee that it works. So I believe the threshold is indeed just n times n minus 1. But yes, with this threshold, if the number is over the threshold, like if the thickness is over this threshold, then I can guarantee that a is greater than or equal to n minus 1, which is greater than or equal to b, which means that this always works. Okay. So here, this is the specific case of I can make this into a 2-1. And so here, in this specific case, n is going to be equal to 5. Oh, sorry. N is, I have no idea what I'm writing. N is going to be equal to 2, which means that I can automatically construct all numbers which are greater than or equal to 2, which is exactly what we need. And that means that it is done. Okay, I'm really curious to see the hand cam. So yeah, but anyways, Zai would have some oh, it's a camera. Okay, I don't know if I can see this. If I split my screen and have like part of the Discord be visible, would that still work, or would it be like janky in terms of?
if you're asking on behalf of the recording, I think I can switch between them. I think this will do.
No, I mean like
Or do you
I'll
mean
have to.
in order for you to see it?
Yeah, so
I
that would
don't
be
know. I mean, if you want to, that's fine.
I feel like it's better if I just switch between the two, but then I don't know. But if I switch between the two, it's a lot of editing. Let me think. I think I'll just switch sometimes, and
Well, I think it says you
I'll
can pop out the stream from Discord.
Oh. Okay, let me see how that
With
works.
that button in the there you go.
Pop out. Oh, right. Okay.
Now maybe do like a
How
half
does
and
that
half.
pop out? I'm also gonna see if I can view at the chat at the same time. Oh, the chat. Oh, this is almost great. I just have to switch, kind of.
Well, I mean, you could just put that on the right half and your Excalibur on the left, but I don't know.
Okay, sure.
I don't know.
That then. I'll have to.
I can also call out chats as they come if you want.
What?
I can like speak the chats if you want as they get sent.
It's mostly I want to see Zai's screen because I feel like that's going to be helpful.
Right, I just mean you can close chat and I'll just read it for you.
Like I'll have to. If I want to look at Zai's. Let me see if I can enter.
No, but I mean, like you can watch Zai's stream. You can just close the chat because you said like you wanted to have the chat open. I'm just saying I can read the chat out loud.
one location, which means that I can't exactly I can't look at it. Like I can't look at the Zeiss stream from my phone, but I think it's I think it will be able to work somehow. Like I think I'll just be able to like not rely on Zeiss video. It will exist. I just won't be able to see it. But y'all can. So that I think that should be good.
Okay.
Okay, so I just won't be seeing Zeiss video, unfortunately.
You can see it on the
But
recording if you want to.
Well, yeah, but I'm just like I won't be able to see it in real time.
Yep, all good. Your
I
your
guess.
recording, your streaming stopped, by the way, in case you didn't realize.
Oh yeah, I did not realize. I guess it would be helpful if people could put screenshots of the stream like every so often, like into the chat, because I can read the chat on my phone. I just can't view the video. So it's like if like you can screenshot like every once in a while when something is done, would be good. Okay, I shall get back to this. We just talked about how here in this scenario we have an L-shaped L tromino in which we can reduce it to a 1 by 2 in which like 1/2 is 2 and 1/2 is 1. And since this is a 2-1 and we prove that n1 can produce all numbers greater than or equal to n times n minus 1, that means that we can produce all thicknesses above 2, including above and including 2. Great. So these are the trominos. Let's look at the trominos. Obviously, first out of the way, we have the ototromino, which is just really a 1 by 1 because scale doesn't actually matter, and 1 by 4 because that's just a rectangle. So these are all natural numbers. Okay, I may as well write the result here. This is all natural numbers from 2. Okay. These two are obvious. Any suggestions for what we will try next? Let's try the T shape. Okay, good. T shape. Anything immediate about it?
We can make a 3-1 box, like a 3 + 1 box.
Yeah, we can make a 3-1 box, and in general, this works for most polyominoes, in which there's like all polyominoes where there's a sticking thing out, and specifically, I can fold everything in here, or I'll just represent it with I cut along this, so the left side is a 3, the right side is a 1, and what that means is that I'm left with a 3-1. And what that means, if you recall, that means I can construct all numbers that's greater than or equal to 3 times 2, right? So that's going to be all numbers greater than or equal to 6. So this is done. What about smaller numbers? I mean, obviously 1 impossible. 2n also works. Explanation?
The little tab on top folds down, and then the two side squares get folded into half squares, and you end up with a 2-by-1.
Yep.
I
Okay.
don't know if I explained that one, but
yeah, you did explain it well. So if I want to fold this down here and fold these inwards, I get a rectangle which is of thickness 2. So this is a thickness 2 solution, which means that I'm able to get all, which means that I'll be able to get all multiples of 2, right? So we know that 2 is possible, 4 is possible. What about 3 and 5? These are all the remaining cases. Oh, right, yeah. These are all the remaining cases, 3 and 5.
I could do 3.
Okay.
It goes
I'm
like
assuming
this.
on the video.
Yep.
Yep.
Yep. You fold two things like this, and then this part is 3, and then you just fold this part 3 times, like that.
Okay. I mean, I'll need somebody to send me a screenshot because it's. I mean,
So
it's technically ambiguous which two
the
folds
two
you're
the two on
making
the
for.
outside get folded in like with a
Yeah,
cut point of
yeah.
unit
It
1
doesn't matter
through.
which part gets folded, but yeah. Just
Yeah, but
fold the
also,
2
right.
outside parts like this,
Yeah.
fold the
Exactly.
remaining part like this,
Yep.
roll it, make a 3.
Yep, it's a thickness 3 solution. Yippee. I just wanted to get the screenshot thing in so I can do it for later things, which will be arguably harder to guess what the solution would be. We can make a 2-1 as well, so we get 5. Explain how that works. So thickness 3 is you fold it into a 1-3, and then the 3-1 will not only give you 6 and upwards, it'll also give you specific values like 3.
Oh, I think I see the 2-1 case. Actually, disregard.
Okay. I see Elliot's solution, and
Yeah.
it works.
Elliot's, yep. Top down, left halved. I don't know if the contrast takes it, but top down, left halved. You fold this again. That's 4. Yep.
So
Now this is
so you-
4. This is 1. You fold this entire thing there. Now this is 5. You fold the remaining part into 5. Did you get that?
Yep.
To swap?
Yeah, it's totally
Yep.
visible.
Yep. 2, and then you would half the 2, get a 4, and the 4-1 will get you a 5. Because if you look at the length of like the strip here, we started with a 1.5, like the length of the 2 is 1.5, and then we divided by that by 2 to get like the length of the 4, and that's within the length of the 1, which means that we will be able to cover the entirety of the 4 with our 1 and have some left over. So this is technically a less than, and then we'll just cramp the leftover 1 into 5. So 5 is also possible. I have a slightly different solution in mind, but this also works. The solution being that if I have a 1-2-1, then I can fold it such that I do I fold the 2 in half and I fold the 1 out, right? So I have 1 and then 2 and then backwards 2 and then 1. This is not the skill. 1 and then 2 and then 2 backwards and then 1. So I have like a 1-5-1 kind of thing. So I end up with 1 1 and then this is 5, this is 1. So that will also work. And this will be the slightly more general case of this. Anyways, now that we've finished the T, let's look at some other tetrominos. The tetrominos are mostly unfascinating, and so we'll okay. We're gonna have the Z, and we're gonna see that everything that we did with the T still works, basically. Yeah, everything that we did with the T, right? So let's say the 3-1. If you look at the 3-1, the 3-1 also works here. So you get 6 and above. 1 is obviously still impossible. 2 is still possible by doing this fold and these in. So this fold and these in. And then 3 is possible by the 3-1. 4 is possible by the thickness 2. I mean, like, if you have anything, then you have all multiples of that thing. And then for 5, you do it the same way. You can do it with the 1-2-1 method, or you can do it with the 2-1 method. Both also carries over to the Z shape. Okay, so let's look at the final shape. I mean, obviously, reflection gives you the same case, so I'm just not going to elaborate on that. Let's finally look at L, which looks like this. I am pretty sure that everything still works, if not even simpler. So specifically, I'm just speedrunning through this. You still get the 3-1 if you just like fold everything in like this. And you similarly, because you have the 3-1, you also get the 3. You still don't have the 1, and you can get a 2 by doing this fold, right? So you get a 2 here and a 2 here. So 2 is also easy, and by extension 4. And for 5, here's what you can do. The 2-1 method no longer works, and I believe the 1-2-1 also doesn't work, but it's just simpler because after you finish this crease, you get a 2-1 that looks like this. You get a 2-1, and you can just fold the 2 into a 4, and then fold it in to get a 5, and be left with some 1 that you can cram into a 5. So that is relatively simple. And basically, to summarize, we found that up to tetrominos, anything from 2 onwards is always possible, and it's trivial to decide if 1 is possible. That's where the good stuff ends, and up to pentominos is possibly undecided shit. And we're gonna look at pentominos. This is where I'm gonna let it be free. Specifically, there are 12 pentominos, and there are a bunch of thicknesses. There are exactly 2 scenarios, and by scenarios I mean like pentomino thickness combinations. There are exactly 2 pentomino thickness combinations that I haven't found a solution yet, and I'm going to allow you all to explore what we have in the pentominos, and I will not spoiler what I think is possible or is not possible. I believe that this is where most of the fun lies. Now we're gonna start off with the obvious simplest pentomino, which is the I pentomino, which is 1 and up. Other than that, there is interesting stuff. Any suggestions for which pentomino we should start analyzing? I mean, there's a 2 in 11 chance that we'll reach a pentomino in which something is undecided.
So das
P
heißt,
pentomino, you love it. Okay. P pentomino. Yeah. Obviously, 1 is impossible. Is 2 possible?
yes, you can fold the right block in and then fold the one that's left over in half.
Right. Yeah, that is the easiest solution to the P. There are more solutions, and if you want to learn all of these solutions, you can probably check out Zai's clock stream, in which I inserted this into one of the clocks. but TLDR, there are 4 other ways in which you can get a thickness 2 rectangle, but I'm not gonna get into them because it's gonna because it spoils a large part of the fun. So I'll say that we'll leave the other as unknowns. Okay, what about thickness 3? Or what about other thicknesses? What are some other easy to do thicknesses? Yeah, every time we have any number, we have any multiple of that number. So all multiples of 2 are automatically resolved. Yes. Okay. Elliot suggests 3. What is that supposed to specifically mean something, or thickness 3 is easy? Wait, no. um Yeah, okay. I'm gonna give you all more time. You don't have to confirm the thickness 3. You can also look at the high thicknesses, like if you want to.
Well, we
Did
can get
we
the-
say thickness 5 is possible? Because that's trivial.
Yep.
Yeah.
Thickness
Did
5
we
is
mention
possible.
that? Yep.
We did not mention.
We can
Okay.
also make a block of 4 and 1, like by
Okay.
folding the top box in and then having one left over.
Yeah. Because there's an extruding piece, we can fold this into a 4-1. Again, looking at this, we know that therefore it's possible to fold everything that is 12 and above. So 12 and above is automatically resolved, and you can also resolve other things. So specifically here, you can resolve like 3n plus 2, right? Because b is smaller than or equal to a. So even if it's 2m plus 2, 1m plus 2m plus 2, 2m plus 1, or 2n, or 1n plus 1, or 1n, these are also resolvable. So plugging these values in, these would be, well, this would be 9 and this would be 5. These are the two which are non-even, and everything even we've already covered. So therefore, what we have remaining is 3, and then 7, and then 11 are the 3 which are remaining. Yeah, we get 5 from a lot of things. Suspecting that the pentominos will require some diagonals. Interesting. Yeah, I think my mind was saying this, but I didn't think I related out loud. Yep. 5 is trivial for all pentominos. And actually, like, I think 4 is also trivial for all pentominos because there's always a piece that's sticking out. But we'll look at these on a case by case basis. But yes, 5 is indeed trivial for all pentominos, and we said earlier that in general, for any n nomino, then kn is always trivial. Origami techniques allowed, yes. Specifically, I'm not even concerned with the actual folding like steps or like the folding transformation. I'm just concerned with an valid end product. So it's yeah. So you can do simultaneous folds and weird stuff. But are irrational folds possible? Like yeah, irrational folds are possible. Like looking at the chat, irrational folds are possible because I mean, for instance, if you really want to, like if you have a rectangle that's like 1 by 2, and like you want to fold this into a thickness 2 rectangle, you can fold this along like pi minus 3 and pi minus 4, and it will still give you like a rectangle which is like uniform thickness. So like technically, if that's what you mean by irrational folds, these are technically possible, and that's what makes proving something is impossible really hard. But yeah, that's what makes proving something is impossible really hard, because there's literally an infinite amount of folds that you have to consider, and you can do an infinite amount of folds, or like a non-bounded number of folds. Anyways, back to the original 3, 7, 11. I'm gonna give a hint to two of these. You can fold a P into a portion which is 2, 1. Right? Specifically, by executing just this green fold, you can get it to be 2, 1, and that will resolve two of the unknown cases. Because I see that we're discussing.
I see how you can make that into 7. So if you fold the 2 into thirds, like into 3 sections, then you can make a thickness of 6, and then the 1 can be folded over top of it, and you can play the same game where you scrunch the end up.
Yeah. So basically, you fold the 2 multiple times until it's either 6 or 10, and from 10 you can get 11, and from 6 you get 7. So let's say if you take the case of 6 and 7, then what you get is, if you fold this into a region of 6, my pen is not working wholly. A region of 6, and then you fold that one up, then you get 7. So the 6 becomes 7, and the other leftover part can also become 7. And so that's a solution for the 7. And similarly, 11 is possible by 5 secting the 2 into 10, bringing the 1 up, and then ending with 11 by 11 folding the 1. So 7 and 1 are possible. What about 3? Okay, I will say 3 is actually one of the unknown cases. So I do not know if it's possible to do with 3. So I mean, if anyone can find a way, that'll be fantastic. But I don't see a way of immediately making it 3. I've tried a lot of reducing by rows and columns, and anything having to do with diagonal folds seem to just not work.
Wait, is this like a problem that you invented? Is there like no literature on this? When you say it's an unknown case, unknown to you, unknown to everybody? Has anyone tried?
This is unknown to me, and I suspect unknown to everybody. I like the case for thickness 2 is relatively known, because it's a superset of folding something. It's a superset of a subset of folding something into boxes, kind of like because if you imagine a box, but the height is 0, then you just get a layer 2 rectangle, kind of. So it's kind of similar to that problem, in which case it's a subset of that problem, in the sense that its height is necessarily 0, but it's a superset of that problem in the sense where folds can go across like the bottom and top of the box, kind of thing. Yes. I am relatively certain that the creator will not be able to join the talk, so that's unfortunate. Like, I would have considered inviting them, but they are not very available for talks. So that is why. I'll see if I can get a time for them. But yeah, I do a lot of work on origami puzzles in general. I contributed to a lot of the problems in the origami puzzle set, and specifically like some of the main set and also specifically the April Fool sets. So that's where you'll be able to find me. Yeah. So, but like I don't classify this as existing literature because almost all of the content of origami puzzles is just like it's a blur in the line between existing literature and what I know, because that's literally just both. But yes, 3 is an unknown case. And in general, it's really hard to prove that something isn't possible. And I think there might be some results in which we can prove that thickness 2 puzzles are impossible to solve, but I'm not sure. As in, I don't know if the proof carries over. It's a long story. We'll get to that. Reminder to self. Okay, how do I remind myself? Reminder to self would be to talk about anyhow. We'll continue. Here I'm not sure if 3 is possible. 7 and 11 are possible. And so 3 is one of the unknown cases. So P pentomino and 3 is one of the unknown cases. So I'll put this as red. Unknown. It's like P pentomino. Well, P pentomino thickness 3 is we're not sure if it's possible. Okay, any other suggestions of pentominos? And the probability has gone down to 10% that we're gonna encounter an unknown case.
I really want to try the U pentomino.
Okay, let's do the U pentomino.
The pentomino that looks like a gun. I don't know what that pentomino is called, but oh well.
I'll try the U pentomino. The gun, you either mean the L or the Y.
The L of a protrusion.
Okay, so here's the U pentomino. Any immediate results?
Well, you can make a 4-1. You can also make a 2-1-2.
Okay, so immediately going to reductions, you have a 4-1 multiple ways by just selecting an arbitrary extrusion. So you have a 4-1. Or if you just reduce it down, then you get a 2-1-2. And so what the 4-1 tells us is 12 and up are immediately resolved. And what the 2-1-2 tells us is slightly less straightforward. But yes, it does have some results. I will propose something that we shall consider first. Is thickness 2 possible? And I'll also accept general vibe based answers.
You can make a thickness 7 one.
We can make a thickness 7. Specifically how?
Diagonally folding the two protrusions. I think it's really hard to do this in a mind. I need a model, but oh
well. You probably want to draw it out or something, or otherwise I completely cannot understand what you're talking about.
You can also tell me what to do.
Oh yeah, you can also. Zai has the power to.
I'll be the avatar.
Like diagonally fold the protrusions into a right angle triangle. Right. and the other one as well.
Oh,
Fold it
I'll be
down.
looking at this video then.
Fold it down. I might be getting this wrong.
I think I might see where you're trying to go with this, Zai. If you could unfold one of them, and then fold the
making it. Oh yeah.
Fold the bottom right corner up and inward before you do that. Yeah, like that. Now fold that down. Fold the whole.
Like
Yeah,
this?
yeah. Bingo. And now that should probably be able to.
This one too? Or
Something-
not?
Is it possible to fold
wait,
the two
no.
protrusions? Is it?
Sorry, you go
Just okay.
first.
You get the talking to. You get the talking stick.
Sorry. I think so, Zai. If you undo the left side. Now fold along the diagonal that's in the bottom left square that you have not yet folded across. The bottom left square, the yeah. So now, wait, that's not 4. Or shut up.
That's
No, I'm miscounting.
That's some.
That gives you
One,
something, but
2, 3, 4.
that's not even uniform.
4.
Never mind.
I believe. Wait. Yeah, it's not uniform.
Okay, I'm going to return the attention to solving this with thickness 2. Which is about solving the U shape into thickness 2. And
Biggest problem with 2 seems like the middle square. You can Z fold it into a layer 3, but that doesn't help us solve 2. And I can't think of how to that kind of fold. Although I was imagining folding the 2 ears, the dog ears, down first and making 2, 1, 2, and then Z folding the middle so that it was like 2, 3, 2. But that's not helpful actually. And I'm trying to figure out how we could pull the 3 out of the middle and only make it a 2. And I don't see how to do that. So I have to determine to say I don't have an answer for that.
Hypothetically, are rectangles with irrational side lengths possible?
I think that's fair game.
Okay.
I say a rectangle's a rectangle. That seems like it should be fair game.
I've got nothing really.
I will confirm that indeed the solution is irrational side lengths, like of the rectangle. So
Wait,
you do have to
already
do
have
that.
the solution?
I do.
Okay.
Because it's the first few diagonal ones I think are much harder to think of. And so it has to do a lot with trial and error.
Zai is doing something interesting.
Meanwhile, I'm gonna talk in the background about like the kind of rationale that goes behind folding diagonally. Specifically, thickness 5 is interesting because root 5 is something that's okay. Elliot, if you have to leave, you feel free to leave. I think you'll be better off just watching the recording. It will be interesting to summarize, I think. But yes, the rationale behind folding diagonally, specifically for pentominos, is because root 5 is surprisingly easy to get with diagonals. If you consider a diagonal with that's if you consider like some diagonals of common slopes, then you'll find that root 5 arises pretty often. And I'm being deliberately vague for a reason that you'll see later. root 5 arises pretty frequently, as well as some other related numbers. And that means that folding it with diagonals makes it pretty likely to be a thickness 2. Whereas if it's let's say a hexomino, then if you have a rectangle that's root 5 by root 5, then that has an area of 5. So the thickness would have to be like a fraction, and that's not really workable.
I'm gonna ask another stupid question. Are squares allowed?
Squares are rectangles, yes.
Okay.
If root 5 is showing up, then I feel like that implies that we're going to be finding like Pythagorean triples of side length 3 and 4, and then somehow doing a diagonal, the hypotenuse of 5. But I'm sketching on some graph paper right now, and I haven't found a good way of doing that with the U pentomino yet.
Well, I think it just comes out from like the root 5 comes from like a length 1 and a length 2. That's the diagonal of like a 1 by 2 box, if I'm not mistaken.
I am going to say that the U pentomino is one of the trickiest pentominos to deal with. With the main reason being that it doesn't actually use root 5 per se. Rather, it uses root 10.
We're solving thickness 2, right?
Yep. This is bringing me back to the good old days of the clock.
Zai, could you fold the bottom right corner to the top left corner of the right square, the right ear? Yes, that one up there. If you join those two together, what's the resultant shape kind of look like?
There are infinitely many ways to do that, so you need to kind of, no, I mean,
Are there infinitely many
oh,
ways?
I mean, no, there's only one way. Wait, but I think that's still gonna include root 5 and not root 10, so I'm kind of...
Okay. I just wanted to kind of look at it. Though
Yeah.
yeah, I don't see what to do with that little dog ear, the little triangle hanging off the end there. So maybe never mind.
To me, root 10 sounds like it has to come from one of the length 3 by length 1
Yep.
sections here, but I'm not seeing how to do it yet.
I think a very cool part of this is like afterwards I'm gonna show a method which makes everything so easy. It's funny. It's also very interesting that it works.
Well, this is very fun, so don't be in too much of a hurry to show that easy answer.
Yeah. Well, I mean, I guess a lot of this is trial and error, but there's like a kind of systematic way of I think it's a systematic way of generating good candidates.
Is that your camera's in focus, by the way? There you go.
And blurry. Okay.
I don't have like I'm trying. This webcam is kind of old, and I don't have any control over it. It just has its own settings.
Can you manually? Is it possible to manually focus it or turn off autofocus?
I want to do that, but wait, I'll try to fix. I'll change my camera. Wait. Maybe I can do share an OBS, share something through
Maybe your lighting.
OBS. Maybe. Yep, I got it. Okay, I'll manually change the focus. Yep, I think that's it. Okay, I think I got it.
Yeah, it's focused
Now,
now.
yeah, now it should be focused. Also, maybe this looks better.
I will continue. I'll continue the app. Well, trying not to give the solution away. The
Can you
solution is indeed just a several like slope 3 or like 3 or negative 1/3 lines, and it's not quite in that proportion, but it's similar. And so it should be easy to get via try and error if you know that.
Does folding does Zai, can you fold the right the one corner of the ear down to the one corner of any ear down to where your like left
You could also like
left
try
index
saying
finger.
in coordinates. Like I think that would be also
So,
like this
sorry,
is
my
0,
English is not
0.0.
that my
I think
English
we
is
can
not that good.
I think we can
Um,
perhaps like write the
So this is
coordinates
3,
on the
2, right? This is 0,
Yeah.
0. Yep, this is 3, 2. You want to fold 3, 2 to where?
3, 2 down to 0 2 down to 0 is 2 2 0 2 0. I'm sorry. Does that accomplish anything?
I think then you want this to be an edge of the rectangle, and I think that's facing too much this way. So I think that might not be it. Like in this case, the rectangle would have to look something like this, I think. Right? If this is
Yeah.
a side of the rectangle. But I don't know, maybe I could try this. And that gives another side of the rectangle, but I don't know if anything can fill in this part.
What about
Maybe.
the other? What about the other side? Like no, do it the opposite way. Like 2 2 down to 0 3.
Okay.
Wait, that's just the same thing. Okay, never mind.
Okay, I'm gonna
I
address it.
think it's gonna look something like this. So I think the resulting square might look something like this.
Interesting.
You see this? This I think is root 10 over 2 by root 10 over 2. If this is possible. Whoops.
Yeah, do a spiral thingy.
Oh my god. That's it.
You got it. You got it.
And yeah, it works.
You got it. That's a geometrically interesting square.
Yeah, very much a geometrically interesting square. It's actually a square that comes up somewhat often if you're into like competition math, like because of like the way it's structured, having to do with
I was never good at
Pythagorean.
math.
What are the slopes of those lines?
It's like 1/3 and 3 and so
Yeah.
stuff like that.
Sunny, is that the
Like-
solution?
Yeah, that is the solution, and that is the solution, as in it's the only solution that I know.
Oh,
And I'm relatively certain that that's the only solution which exists, but I'm not sure. All right, so let me draw. The solution is okay, I'll have to blow up this shape, otherwise it's not going to work. So if you have a U pentomino, then what you want to do is, oh my god. Then what you want to do is make these folds into here, such that, well, you can see that how the erected resulting rectangle, or here it's actually just a square, arises, and one way you can have it is to be here, so like this square. Okay, and now I'm going to talk about how you solve this in a kind of trivial way, and by trivial I mean using some interesting ways of generating plausible candidates. Okay, here's the way. Okay, think about tessellations of this U pentomino, which I know is out of the blue, but hold on. Think about tessellations of this U pentomino across the plane, right? Now, some of these tessellations will work, and some of these won't, which is why there's like an iffy part of the construction. But one of these tessellations look like this, right? So we have U shapes up here, and like this continues, etc. But we don't really care about that. We'll just focus on one strip. If you look at how these creases go into the tessellation, you'll find that they resemble straight up a square. And specifically, like even if you go into this, that's just another square. And this is what this really is a square tiling of the shapes. I don't know if this is clear enough. I hope this is. So what you kind of have is like a slope, a square tiling of the plane, overlaid with the P pentomino. What this therefore means is that when you fold it into a square by just following the creases on one of these shapes, it works. And the reason is the following. And this is the otherwise
When you
GT.
said P, you mean U, yeah?
Pardon?
When you said P pentomino, you mean U pentomino, right?
Oh, sorry. Yeah, U pentomino. Yeah. Well, for these U pentominos, look at how this creates a strip, right? So if you think about it, this strip can be kind of neutralized if you fold the ragged edges together. So you can think of how what we're really making is a kind of torus shape, right? So two U's would create a torus. Right, two, as in two U's would create a part of the torus, because this infinitely extends. And the way that we can fold this torus into a rectangle is by neutralizing all of the edges, or basically by finding where the next part goes and folding everything in half, right? So I can do this, I can do this, I can do this, I can do this. And essentially what this allows us to do is, if I can fold this like in an arbitrary manner, if I fold this along this line, then I can get this to like translate over to here. I can get this to translate over to here if I fold along all of these lines. So what I end up is a perfect thickness 4 kind of tiling for 2 of these pentominos, and for a single one of these pentominos, that would be thickness 2. So that's a rough heuristic for how it works. This is not a proof at all, and sometimes the tessellation method doesn't work. But this is a nice heuristic for how to generate these diagonal things by considering tessellations and then looking at how we can neutralize the ragged edges. Is this somewhat clear, if insane?
That's pretty clear. And are you saying that this generalizes not all the time, but often to other pentominos or n-ominos? Because
This
it seems like it would.
Yeah, this is something that generates a lot of plausible, a lot of plausible solutions. It doesn't quite work all the time because of because even if I can tile like if I can fold 2 U's into thickness 4, doesn't mean that I can necessarily fold like 1 U into thickness 2. But the rough essence is that this works.
Got it. Okay.
Okay.
Well, I've got my graph paper ready to do some sketching of tessellations now.
Yeah. Okay. So if we look back at the P pentomino, there's something similar that you can do to the P pentomino, which is tessellation. So consider this tessellation. And this is actually a simpler tessellation because we don't need the flipped version of the piece, right? So here we needed a flipped version of the U piece, but here we don't even have to use the flipped version of the P piece. Of course, if you want to, you can still do it, but it's no longer necessary. So here we'll have this jagged edge, which we want to neutralize, right? So look at this jagged edge that we want to neutralize. We take like midpoint of these and we connect these. So that's one way that we can neutralize these. And then starting from this, we can start building our rectangle. So if like this is here, so I'll build it out here, and I'll build it out here, and I'll build it out here. So this is how one of the foldings for thickness 2 would work, right? So you would fold along these creases, like these creases, and you will be able to get a thickness 2 rectangle from this P piece. You'll also find that the P piece has more than just these tessellations, and the tessellations give you multiple different solutions to the thickness 2 puzzles. And you're welcome to try these yourself afterwards to see what interesting other solutions to thickness 2 you can find. But P piece is one of these where there's a lot of solutions. Okay, we're really starting with the hard stuff, huh? Okay,
Hard stuff.
so U piece. Well, U piece, we know that now 2 is possible. So by extension, all multiples of 2 are possible, which again leaves us with 3, 5 is trivial, 7, 9, 11, and these are 3, 7, 9, and 11. And in fact, 2n plus 1 would give us 9. So specifically, if you fold this into a 4, 1, you can bisect the 4 into 8 and then fold it to get a 9. So 9 is also easy. What is left are 3, 7, and 11. These are the 3 cases. What do we think about these cases?
Sorry, can you repeat what the check mark next to the 9 means?
Oh, okay, sorry. We mentioned earlier that you can reduce this to a 4-1, meaning that you can fold everything together except one square. So you get a 2-square combination with a 4 and a 1. And that means that you can fold the 4 in half to get 8-1. fold the 1 over to get 1 9, and then fold the 1 into 9 pieces to get 9.
Oh. Huh. Interesting.
And this also generalizes to all numbers greater than or equal to 12, because you would fold 4 into like some multiple and then fold the 1 over enough number of times, and then if there's any remaining ones, then you have to deal with that.
And that seems to work for the P as well, because the first step is also doable.
Yeah. So now we're left with 3, 7, and 11, which are the 3 remaining cases. What do we think about 3, 7, or 11? I'll give a hint, which is that there's something you can get, which is called a 3-1-1. Which allows you to make 3, 7, 11, whatever you want.
I mean, is it just simply folding it into like an L triomino?
El triomino, and then what? I'm not
Why is
completely
that?
sure.
I was wondering if that's what a 3-1-1 is.
Not El triomino. No.
Okay.
Okay, so here's what this means. When I have a U, I exercise these two folds. This and this, I fold these all together. So what I now have is a 3-2, but the 2's are independent. So I could move these 2's differently. So I have 3, and then I have 2 1s, which are independent. And this allows me to solve 3, 7, and 11. Any ideas of how?
Oh. Shucks, I thought I saw 3, but no, I don't.
I was thinking about this earlier, and I thought that you would be stuck because of the two, the
I
1 and 1
think
on top of each other. You'd be stuck with an even number there, no
no,
matter.
yeah. I think you can fold the 3, like the 2, one of the ones on the right, you can fold it in half, and then like you can scrunch the remaining little section of 1. Yeah, exactly. So now that 1 keeps, yeah, perfect.
Yep.
Oh my gosh, it's perfect.
This is the solution, which is if you have 2 1s which are independent, this is super versatile because you can use the 1, you can waste the other 1 by just crunching it into the 3, and then for the remaining bit, that's also a 1, so you can just crunch it into another part of the 3. This will also apply to 7 and 11 in differing ways. Specifically for 7, what we have is we have the 3 roll over, so this is like 6, and then I have 2 1s, right? One of them goes like this, one of them goes like this. The rest is trivial because I have a 1-7-1.
Nice.
And I can just crunch the 1 and 1. For the 11, well, I do 3 then, and then I do 3 back, and then I do 3 forward.
Yep.
So now that's a 9. And I have 1 here and 1 here. So I do it like this, and that's the part of the 1, and I would have a 1, 11, and a 1 remaining, and this will also be easy. So these are all originating. Oh,
Wait, sorry, don't those end up on the same side, the 2 1s?
yeah, sorry, that's my mistake. The same works. Yes, I did mess up. Okay, let me re-explain. What I will do is I will fold the 3 into 6s. The 1s are on the same side, so they should actually look like this. And what I drew earlier was incorrect. For the 7 case, it's the same thing. You have 1 on this side, 1 on the other, and that gives you a 1-7-1 with like some remaining. You can check that it's like remaining. For the 11, it's like different. You have this 9, but you also have 2 1s over here. What you can do, well, is you can get one of these ones to go like this, and that gives you an 11 1 1. 11 1 1. Where the 1 is not of the same length, but it doesn't matter. So here you have 11, and you can check that there's like some remaining over because this length is going to be 1 over 3. That's probably not the best way to write it. This length is going to be 1 over 3. And so there's going to be some length over here that's remaining, specifically 1 over 3. And what you can do is you can tenfold this such that if this is like 10, there's one extra layer down here. So that's 11. And you take the remaining stuff and you bunch it into 11 bits. So 11 is also solvable. And in general, if you have something like n11, that's a strong indication that you can do a lot of stuff. And specifically, I believe n11 is as good as n is as good as n1 because of the similar way and how this works. Yeah.
Okay, so we've
going-
completed the
Yeah.
U, the
So
U.
we've completed the U. 2 and above are all possible. Okay. We really do be starting with some of the craziest pentominos to select. Okay. Any suggestions?
The wait, what's the the R pentomino?
The R pentomino. I don't actually know what the R. I think there's like one terminology. I think it's like a terminology that I don't use.
The R pentomino.
Oh, okay. I would use like I typically use like the notation on the top one, so it would be like the F pentomino, like for me. But okay, I shall do that.
Both variations. Oh wait, there are no variations. Okay, I'm sorry.
And we'll start with thickness 2. What do we think of thickness 2?
Well, you can fold the right bit in and the left bit in, and then the bottom you just fold in half, and you get like a 1 by 2.5 exactly.
So you get this, and this is solvable thickness 2, and therefore also by extension solvable for all 2n. What else? Well, okay, we're just gonna save time here. I'm gonna speed run through this because this is mostly an easy case. What I have is a 2-1, right? So what that 2-1 means is that's exactly the same scenario as the one in the P pentomino. So I will be able to resolve all of these cases as well, meaning I'll be able to resolve any cases 12 and up because that's just a reduction from 4-1, and then I'll also be able to do I believe 7 and 11, and also 9 because 9 going from the 2n plus 1 of 4-1, which means that and also 5, which means that all I'm left with is thickness 3. Can I do thickness 3? That's the problem.
So you can do this. That gives you 1, 3, 1. Just roll it. Roll the top one down. Roll the bottom one up. You
Yeah.
get 1, 3, 1.
Yep, we roll everything together, and this is what I just call by we collapse all of the columns, so we just get 1, 3, 1, and we can fold the ones, and we can fold the ones on both sides to get a 3. Akiva says there should be some way to write a program. It's just the fact that things don't have to be necessarily at nice looking places for them to work as folds is like the main problem. So F pentomino is solved. Well, I guess. Well, so we're 4 pentominos done. What next?
This feels like Zai's flag video.
Alright, that's like okay. 4 out of 12 pentominos complete. 33.3% of the work done. I'll have to pull up the actual like this. Let me find. Oh, oh god, this is okay. Finally, okay. 4 out of 12 pentominos. Okay, that's not okay. There's nothing that's interesting. Yes, that is a progress bar, and you are 33.3% done.
Did you translate this into Tokipona?
Not even close to all of it.
Oh no.
And also not just me.
Sonny, I
a
thought
lot
you were
of-
supposed to be good at Tokipona.
I'm actually not good. Like, I'm actually super not good, considering
Why do
what
you-
I mean.
Why do you have Zai's script as in this Excel sheet?
To translate. Anyways, we're getting off topic. We shall return to this.
All right, let's just go with an easy one. I want to go with like the L, like the long L. It's like 4 with 1 sticking out at the end. It seems like it should be pretty simple.
Okay, let's do thickness 2.
Oh, I was gonna say the other L, but that's fine too.
Okay.
Like the long one.
This one is technically, I think, V. Well, L. Whoops. Well, let's speed run through this. Thickness 2 is obvious because you get, you just fold this down, and then this right. So that's thickness 2 done, and an extension, all even numbers. What else? We can get all things 12 and up because because you can get into a 4-1. Right? And that grants you everything 12 and up. So what do we have left? We have 3, 5, 7, 9, 11. Again, 5 we know because it's trivial by pentomino, because it's a pentomino, and 9 because it's trivial from 4-1. Now we have 3, 7, 11. What do we think of that?
Well, 3 is easy by just like folding the little block down and then folding the whole section over.
Yeah.
So then you get like a 3 and then a big section of 1.
You just have a 3-1, which is just better than a 4-1 in every way. And in fact, you can also just use a 2-1. And well, okay. The reason why this 2-1 doesn't allow us to use the lemma from earlier is because this specifically the 2 is longer than the 1, which means that it doesn't exactly apply. But if the 2 is shorter than the 1, then it definitely applies. So we can just apply the lemma from earlier, which is to say that everything greater than or equal to n minus 1 is constructible. Oh god, no. Okay, everything starting from n times n minus 1 is foldable. And therefore it is possible to get everything that's 2 and above. And that is just the easy part of this. Let's look at the because I was drawing the V pentomino because I saw somebody in chat talk about it. Let's look at the V pentomino. Let's look at T2. Thickness 2. What do we think about thickness 2?
Well, I don't know. I was gonna say something about being able to construct like a 3-1, but that doesn't help us with thickness 2.
Okay. Yeah, it is true that we can construct a 3-1, because the 1 is longer. That grants us some access to specifically everything 6 and above. So we all just need to consider the cases of 2, 3, 4, 5. 5 and 3 is obviously trivial because you can just cramp the 1 into 3, and 5 is trivial because it's a pentomino. So realistically, we have thickness 2 and 4 left. The 4 is also easily doable. What do we think of thickness 2 for the V pentomino?
I think I've got 2. You can just start at the 0, 0 corner and put it to the 1, 1 corner, and then do a series of diagonal folds. That.
Okay.
Oh wait, maybe that doesn't leave you with an actual rectangle. Damn, so close. Never mind. I'm gonna keep
Okay,
working it.
what did you mean specifically?
I was thinking
I
that
just
you
did
could.
it. Yep.
Go ahead, Zai.
Yeah. It was this, right? You were thinking about this. Like that. But then this doesn't work because after you do this, this gives you 2 squares.
That is
overlapped here.
not exactly what I was thinking, but it fails for a very similar reason in that it's not a perfect rectangle at the end. I was trying to make
Yep.
like a very long, thin rectangle instead. And so if those, your first fold is correct, and then if the next 2 were orthogonal to what you had, basically one fold across those 2 squares, then you would start getting like a long, thin rectangle, but it ends on both ends with the same right 45-degree non-rectangle corner. I was very excited for a second though, because I thought that it was working until I started folding a real piece of paper.
I'm looking at the tessellation, or at least the one that I was able to come up with, and I don't see an easy way of making it have the right slope such that you can just continue packing pieces in the right way that it would align with the same like squares as we discussed earlier. No, Zai, it was not the one that you were just pointing at, but it was like there's like 2 of them and they're kind of like staggered. But yeah, maybe there is a way of doing this that I'm not seeing off the top of my head to make a tessellation that goes the right slope.
I'm interested in Sawdust's idea. Zai, can you fold what Sawdust meant? As in, like fold 0, 0 to 1, 0, and then continue folding, but like the 2 folds which are present should be this. Like this is a very similar idea to the actual solution. It's slightly off, but it's somewhat recoverable. Like the current folds are not correct per se, but they express a very similar idea to what the actual solution is.
Yeah, I think in the end you shouldn't get this because if you get this, that means the rectangle has to be this, it has to align here. And I think the center of that rectangle should be this point. So this line maybe. And then we would be able to just fold this part in and that would complete the edge of the rectangle.
What pentomino are we on right now?
V.
V, okay.
Okay. We'll wait on a moment.
Oh, I like where Zai's going. That looks like it works. Check that out. It's beautiful.
Yep, and indeed that will just work.
What are the dimensions of that? I missed it.
What are the dimensions? I think this is root 2 over 2 by 5 over root 2 over 2 by 5 root 2.
Huh.
Nah, 5 root 2 over 2. So then that will multiply out to be 5 over 2. So that's a rectangle of the thickness 2, originating from an area of 5.
Wow.
So is this a general solution?
Somewhat. I'll explain further. But let's look back at the tessellation, and I'll draw on mine. Here's how the tessellation looks, or at least one of the tessellations. I believe that's the only tessellation, but I'm not sure.
I found a couple tessellations.
Oh, okay. Never mind. Here's the tessellation that I have in mind, which is also, I believe, the easiest to conceive of.
That's not even one of the ones on my list.
Okay. Here, what you have is this kind of tessellation. And looking at the ragged edge, we use the same neutralizing idea that we have, which you can neutralize by looking at this line, right? And this line neutralizes, so you extend up to get this. And you just, from this, you just complete the rectangle. That's one thing that you can, so this is another thing that you can do with tessellation. And very good question by Jennifer. Is this generalizable? I'm very proud to say yes. This is generalizable to a lot of polyominoes, actually. So I can draw you a seemingly arbitrary polyomino like this, and I can promise you that it will be able to be folded into thickness 2.
Okay, so are there polyominoes that can't be folded into thickness 2?
Okay, but this isn't just an arbitrary polyomino. Okay, so here's the fold, which I'm gonna draw. But it looks like this, and I believe the idea
Get a
is
drawing tablet.
where am I even at? And this would be the rectangle. And how it's gonna work is that if you only go like, it's kind of like if you only go starting from one square, and if you only go down or to the right, then necessarily the shape that you're going to have is going to be able to be tiled in this way, tessellated in this way, and the resulting rectangle will always work. And so that's the result. And this is the way in which it is generalizable to all polyominoes which are kind of like one wide or extend only in one direction. Okay, does that make sense?
Okay.
I'm pretty sure there are
Can you
infinitely many
remind me-
tessellations.
I did not hear any of the other things. I didn't hear much of the talk.
Can you remind me if the other tessellation that we saw had one chirality, or did it have reflections of the pentomino?
Some of these require reflections and some of these don't. So like for the U shape, we had to use for the U pentomino, we had to use the reflection because it was well, I think of rotation and reflection as both being changes. I think no, there are no reflections involved. This is a rotation by 180 degrees. If that's what you're asking.
Okay.
Yeah.
I wasn't asking about chirality. I meant to ask about like rotation, because
Yeah.
it seems like if they can tessellate without rotation, then it should be pretty easy. We're able to tessellate without rotating. I suspect that same concept that we see down and to the right with the V pentomino will work similarly. But again,
It will work similarly for many other pentominos as well. So
I mean, it obviously works for the ones that go down to the right, but I'm imagining like a kind of awkward anomino that doesn't have that property of only going one direction. Anyways, just something to think about.
I don't know. I will think about that. Anyways, here is the V. We've already done everything. Well, it can reduce to 3-1, and it can also do 3 and 5, as we've seen like from the 3-1. It can do everything 6 and up, and we've shown that it can do thickness 2, and by extension thickness 4. So 2 and above. Okay. Before I forget, how many have we done? Well, we've done the I, we've done the P, we've done the U, we've done the F, I believe. Yep, we've done the F, done the L, done the V. So 50% of the way there. 6 out of 12 pentominos remaining.
You have to do the Zai voice.
Nah. Okay. Any recommendations for what next?
Well, since we're already talking about things that go like left, like or like down and to the right, let's just do like the W, I guess.
Okay, let's get the W. I'm loving this. Here's the W. What do we know about thickness 2? Yay.
It's doable.
It's doable. Yay. By extension, everything that's even is doable. Additionally, 5 is doable. This is reducible to a 4-1, and therefore everything 12 and above is doable. And that leaves us with the usual suspects, as well as 9 is doable. And that leaves us with the usual suspects of 3, 7, 11. What do we think about these?
You can do 3 like this.
Okay, I'm going to look.
Yep. Just do this. Do this. Now it's 1, 3, 1, and then wait. I brain farted. It's not that. It's not that. False alarm.
Okay. Well, I'm gonna show that 7 and 11 are doable first. By reduction to 2-1. If you fold everything down, you get 2-1.
Yep.
That gives us 7 and 11. So that's how 7 and 11 can be done. What about 3?
I'm not sure if this will work, but Zai, could you try something for me real fast? Fold the 2 bottom bits of the W upwards. Not like that. Sorry. Hold the W like no, not like that either. Yeah, like that. Yeah. Now diagonally upwards. Yes. Now fold them both inward up towards the center square. Yeah, like that. No, that's just 1, 3, 1, but more complicated. Never mind. Um, hmm.
Oh, thickness 2.
I'll say
looks...
that this is one of the cases which I haven't solved, but you're free
Oh,
to
shucks.
continue.
Okay.
That and the reason being that this is extremely similar to the case for the P pentomino, because that's also thickness 3. I feel like it's the W is somewhat less constrained than the P, but I haven't been able to find a solution in either case. A large part of it, I think, is the fact that there's not a lot of rows or columns that are reduced to 1. Like, there's not a lot of rows and columns that have like 1 exactly. So that's a huge part of the problem. And the overarching problem with diagonal folds as like in general is that uh to like complete the diagonal you kind of need a thickness of 2, and in either case it ends up being even, and 3 is just weird. I'm happy to give you all the time you need / want to continue trying this. I don't personally believe very strongly that it's impossible, but I haven't been able to find a solution.
I got nothing.
It seems like a very strong statement that if and the correct one as well, that if you fold along any diagonals, you necessarily have to end on an even number. So if you could do some diagonal folds and end up with like a 2-1, for example, then we could get to 3, assuming the 2 is like smaller than the 1. Um, but it seems like it would be impossible to do that on this. Excuse me, on this W pentomino. Sorry, it's food time for this cat. Don't mind him in the background. I feel like it might be impossible to do 3, for the reason that a diagonal fold kind of necessitates an even number. And I don't think it's possible to end up with like a nice small compact, you know,
Yeah.
1/2 by 1 next to a 1 that you can turn into a 3-1. if that makes sense.
Yeah. Yeah. Also cat. Anyways, I'm going to continue. And of course, you're wrong page. I'm going to continue, and we're going to assume that all cases 2 and above, except 3, are possible. And we don't know about 3. And similarly for here, I think I just didn't write the conclusion. But yes, 2 and above, except 3 are possible. Okay. Well, now we've done 7 of these, from 6 to 7. What next?
Let's do the Y.
Do the Y. Okay. Let's look at the Y. What do we think about the Y?
Well, the first thing I see is we can get a 3-1-1, which seems quite useful.
Well, yeah, we do have a 3-1-1. But we have better.
I guess a 1-2-1-1 is strictly better.
Yep, a 1-2-1-1 is strictly better. I would just analyze what a 1-2-1-1 can do, but we can reduce it to a 2-1. So
Okay,
I
yeah,
would
true.
rather just look at a 2-1 and be grateful that the universe has blessed us, because the 2 is shorter than the 1, therefore everything 2 and above is solvable.
Cool. Easy peasy.
Yay. That is super easy. So imagine my surprise when we're getting some of the worst pentominos at the very start.
Oh, that was by design. I knew that you would be hard, or I had a gut feeling it would be hard, so I picked it.
Yeah. Oh, makes sense. Okay. What else?
X.
X. Okay, this is one of the more interesting ones.
So I see a 1-1-3-1 right off the bat.
Yep. We have a 1-3-1, which we technically haven't analyzed. But we analyzed with a 3-1-1. Oh, the fact that we just care about rectangles other than squares is really helpful. Yeah. Okay. Right off the bat, there's pardon?
This tessellates.
Yep. Just let me finish. This goes into a 1-3-1. I could analyze what a 1-3-1 can do, but I'm first gonna analyze what a 4-1. I'm first gonna write down what we know that a 4-1 can do, which is 12 and above, and we'll look at the other cases later. So, what do we think about this thickness 2? Because if we know this is solvable for thickness 2, that gives us a lot in terms of what we can do for other thicknesses. And you know what thickness 2 means for an ugly looking shape. Going to be switching over to Discord here. I will say that there are 2 solutions for this, and one of these is more interesting than the other, I think, but completely subjectively.
I think I see one that almost wants to work. I think I can get 4, like 4n, but I don't know about 2. So like if you draw just naively on top of the X shape, you just kind of draw a square that's tilted, such that it's like touching like it's just a square that's tilted within that envelope, then you fold it in half, then that gives you the right shape. No, that works.
This tiling is useful for cactus farms in Minecraft, so true. I mean, I don't play survival at all, but I know that it's a thing. Yeah.
It's also useful for playing Snort.
Okay, I have to search what that is.
I'm gonna give a talk on
the
it
game.
not too long from now. Snort game. It's the second one in the pictures there.
Second one. Okay, what is it? General. Okay.
So two different colored players are placing pieces on the square grid. It can be any graph really, but the rule is that you cannot place adjacent to your opponent. You can play adjacent to yourself, and last player to move wins.
You can play adjacent to yourself, not adjacent to. Okay.
Yeah.
Interesting. I see. Looking forward to that talk then. But anyways, here is the rectangle. Now, this is what I mean by the slightly subjectively worse solution. And I will share the other solution on screen, which is definable. Actually, do you all want to take some time to attempt to find it?
Yep.
Wait, sorry, we're looking for one
There-
worse than this?
A one that is better.
One that's
I
better
think.
than this.
I'd say it looks better. I mean, I think any hint will sort of just give it away. So I'm just gonna say I think it's subjectively better than this, and I think y'all will agree. It also has to do with the tessellation. It's kind of the same tessellation, but not exactly. Let me just make sure that I'm not randomly saying stuff. Hold on. Let me fact check that it arises from the. It can arise from the tessellation. Okay, yeah, it can arise through a tessellation, but it's in an interesting way, I think.
I think I might have found a different one, but I'm not sure if. I'm trying to convince myself that the one that I found is actually different than the one we just did. Zai, would you help me out real quick?
Yep.
So the idea is basically use the same tessellation, but just like offset the square by, by one.
Yep.
So the actual mechanical way of doing this, starting from like if 0, 0 is the bottom left of like the whole shape, then you're gonna start in 1, 1. And make a line down to 3, 0. Yep. Now fold that upwards along that crease. And now I think you'll fold the little tiny flap on the right side there. Yeah, that'll fold down. And yeah, so now the along the same crease that you just folded the tiny flap, also fold that one. Yeah. And I think
Wait, I think I may have done it like two in. I don't know. I think. Huh. Wait.
Yeah, it is
it because
doable with.
Yeah, is it
It
just
is
because I
technically
did it
doable
not
with
in a very good
tessellation.
way? But
It is technically the same tessellation. It's just interesting in how it works.
are you suggesting that this is it?
I don't think this is it, because I don't know how I would fill this part, because this doesn't really work. Because
why
this,
does it not?
as you can see, it
Oh, wait.
they
Oh,
have
yeah, you're
different
right.
angles. I think what you
Oh.
have to do, yeah.
Wait, don't you follow the same? Try following the same angle.
Like this.
No. The same angle, not like the same angle rotated 90 degrees, but
Yeah.
like the identical angle.
Gives you this.
Yeah. So now fold the square on top down into the. Yeah, like that.
Right.
And then I guess maybe there's nothing to do from here. Maybe that doesn't work. Shucks.
I think the solution would be to like not think about this line, but rather just take this point and fold it into the center, very center. And I think that's gonna be it. Maybe.
Oh, you might be right.
Did I?
You might.
I'm not
You
sure
might
if
not be
that
right.
is. I'm not sure. It's because I.
Oh.
But maybe it is right if I.
Yeah, no, that does look right.
Do all these little parts down. Yeah.
Yeah, it is
that
indeed
gives
correct.
you a square.
And I
How did
think
you-
you will agree that this is somewhat better than the other solution.
Wait, so what's the difference in the tessellation there? Like, what did we change?
That's the interesting part. The tessellation per se didn't change. And here's what I mean. I'll start changing. Anyways, I think this tessellation is subjectively better because it is more symmetrical, and also like the windmill kind of thing is cool. I think we can agree that this is more interesting. Anyways, here's how the tessellation works. So I'm gonna draw a T. Oh my god, this is refusing to cooperate. Okay, I'll do it the hard way. Here's what I have for a T. Here's what I have for an expentomino, and here's the standard tessellation. Right? So we take this strip, we neutralize the edges, and we get this. If we want to neutralize, we get this, down, down, and this. And this just gives us the solution to that, as Dr. Zai has put on there, and then like part of the scratch work. However, looking back at this, there is a separate thing which we haven't considered, which is that while it is true that this is like the only tessellation of X, the X pentomino, it's not necessary that we choose that specific strip to work with. And in fact, there's a slightly more interesting strip we can work with, which is if you look at these three X's, right? These also form a kind of tile, like a strip-like pattern, even though it's not exactly the same. So if we consider these, then let's think about how we want to neutralize this edge, right? To neutralize, you'll find that we need to take what? Okay. To neutralize, you know that, okay, since this center goes like from here to here to here, we know that the edge will have to be in a similar fashion. And you will find that this edge is the one which neutralizes the edge, as in this one is the one which leaves the same area outwards as the area that's missing inwards, or you can just calculate it directly by looking at how wide they have to be, because you know the height of the like one dimension of the rectangle by how far these are spaced. So you get this neutralizing line, which if you extend back into the rectangle gives you the square. And this is how you can get the other folding, which is done with this. And this will look kind of cool. It's definitely one of the cooler ways to do it. Okay. And that is the thickness 2 solution. And now that we have the thickness 2, we also have thickness well, now that we have thickness 2, all that we have left to consider are 3, 5, 7, 9, 11, 5, and 9, which we know are easy to do. 3, 7, 11, which are all easy to do with 1, 3, 1. Specifically, for 3, you just cramp the 2 ones. For 7, you take the 3 and then you let it wrap back around, and then the 1 goes in the other direction. That creates a 1, 7, 1. And 11 is similar. You have a 9. You have 9 here, so this goes here, and then that one will go like that. That one will go like that to get a 1, 11, 1. So that the 11 is done. Okay. Nine pentominos complete. What other ones do we have left?
Let's do the Z. I'm not sure if that's actually the name, but it kind of looks like a Z.
Okay, you are either talking about the M pentomino or the Z pentomino, but we're gonna assume you mean this Z.
That was not the one I was talking about, but let's go with it.
Okay, sure. Let's talk about the Z, and we'll talk about what I assume you're talking about is this.
Yep.
And we'll talk about the N next, and this is the N because it is. I have no idea why. Okay, thickness 2.
Thickness 2, we have trivially on both of them because of the same argument from before. Maybe not trivially, but we already did it.
Yeah, we did it from earlier because going right and down.
We also have 1, 3, 1 on the top one by collapsing the columns.
Yep.
So I think that does pretty much exactly the same as what we just got for the X, and we're just done,
Okay.
right?
Yep. Yeah. With 1, 3, 1, we get exactly the same thing as we did with the X. With it like 4, 1 resolving most of the cases, and
we still have 5 and 9 left. Maybe 5 is obvious.
So 5 is because of pentomino, and 9 is because of 4, 1, which is because of 1, 3, 1.
Okay. Yeah. Cool.
So 1, 3, 1 means that we've done all of these. Okay, I should probably write the end result. The end result, 2 going up to infinity, 2 going up to infinity. Here you can just do a fold down and a fold here, and that gives us this with 2, 1, and that is thickness 2 and everything above solvable because 2 is shorter than the 1.
Sweet.
And that is basically the exact same as what we did for the Y, which is reasonable.
Now we just have the T left, right?
Yep, and we have the T left. Okay. The T. What do we think about thickness 2?
Always got to start with the hard one.
Well, I mean, yeah, basically. So I'm gonna look at the Discord. Assuming that's got interesting stuff. I will say that for the T pentomino, the thickness 2 also has to do with tessellations. As is probably expected.
I was thinking about the W case for a while now. I'm gonna put this here, and I'm gonna think about it. Think about the W case. So if anyone has ideas on the T, you just tell me how to do it. Okay? Just I'll just do as you say.
Zai is our resident avatar now. I'm confused. What pentomino are we on?
Oh, T pentomino.
Like right now?
Yeah,
Okay.
and specifically thickness 2. I mean, gotta start with the hard part.
Tessellations. Does this have to do with tessellations?
Yes.
I see a tessellation, but I don't think it could. I see one tessellation. I don't know if it's infinitely extendable though. Hold up, I need a drawing thing. Everyone needs a drawing thing nowadays.
Yep, this is the tessellation that is useful. And you can neutralize these edges. I will draw the solution. Unless, does anyone want to think about it more? Or
I've drawn like 4 different paths through this thing, and I haven't found one that works yet.
you want to continue trying? Or
Nah, it's okay.
okay. So here's the tessellation as provided by Sawdust. We have this T, we have this T that's on the other hand, and then we have another T. This is getting cramped. And then we have another T in here. And what you can do is you can neutralize these edges with this. This is bad. Neutralize these edges with these lines and completing the rectangle, right? And because here's how the neutralization ends, we know that this has to be root 5 over 2, and so this one has to be root 5. So we complete the rectangle, and that ends there, and that ends here. and this will work. If anyone wants to try that out, or if Zai wants to draw that out.
Okay. That way, okay. So root 5 that way. Just this.
I'm coming here.
So is it just this, or do I have to move it a little bit over?
This is good. And
Okay.
just completing the rectangle from here.
Whoops. Okay, let me make it a bit better.
And that is the rectangle.
Slightly off, but yeah, assume it's perfect.
Of zooming
it's
perfect
perfect.
tools.
Yeah. Imagine this is perfect.
Snaps.
Yeah. That's a rectangle. That's a rectangle in my book. Yeah.
And this is 12. So, recap.
Yay!
12 pentominos.
Well, we
pretty
didn't do the
much.
131 yet, but yes,
Yeah.
you can get a 131, and that'll, or sorry,
I think
311. I
finally
mean,
get to sleep now.
131 as
get to
well.
sleep now.
Yeah. So you get a 131. And then with the similar logic to the X, you have T2 and you have thickness 2 and you have 131. This gives you everything 2 and above. Which means that, to recap, we have almost everything except 5p, like the pentomino, the p pentomino thickness 3 is unknown, and the w pentomino thickness 3 is unknown. Interestingly, note how every pentomino is solvable thickness 2, which I think is kind of counterintuitive. Meanwhile, only a majority of the thickness 6 only the majority of the thickness 6 polyominoes are solvable with thickness 2. I leave that as an exercise to the reader, or find it on Puzzling Stack Exchange.
Puzzle
where
stack
I-
is that exists.
where I post somewhat regularly. Which is more surprising because consider the fact that now you know about tessellations. It is well known that all hexominoes are tileable. Can tile the plane. This is interesting. All hexominoes can tile the plane, but not all of them are solvable thickness 2. This is a corollary of the Conway's criterion for tileable shapes. Anyhow, we have 2 unknowns, but otherwise everything in this world is good.
Yay!
Yay! And
I can finally get to sleep. I can finally go to sleep now.
This is all I have prepared, other than 2 things. One of which is this reminder. Yeah, okay. To get to this reminder. I want to thank a lot of people going into this talk who made this possible. My friend Omega 3301, who I met over on Discord for via interesting means, and introduced me to origami puzzles, and that's entirely why I am where I am right now. Without them, I would not be here. Yeah, this is like a lot of interesting things has happened since then. And one of the interesting things happened was one of the professors from from a university came to us and was like, "Hey, do you want to like talk more about this thing?" And specifically, we were wondering about like one part of it was wondering about. Thank you. One part of it was wondering about what we can accomplish with thickness 2, or how do we prove that thickness 2 is impossible. Basically, improving that thickness 2 is impossible. One result is, I can't remember what theorem it is, but it's, if you want to search for it, it's in geometric folding algorithms. GFALOP, geometric folding algorithms. Linkages, origami polyhedra, which you would imagine to find this related to origami, but this is actually relating to polyhedra. This is about how you can fold something into polyhedron, and specifically into boxes. And one of the theorems was that for something to fold into a box, there always exists a set of crease patterns such that all the things that you need to consider are lattice points and midpoints, I believe, or something along that line. And if we can get this to work with this problem, that'd be insanely good. However, what doesn't apply for like in terms of origami into double boxes is double boxes are like double boxes are like doubly layered rectangles are boxes with zero height, but topologically there's still 2 layers of paper. However, with origami, technically speaking, what you can have is you can have one of the layers of paper, but it goes down into the other, whereas the other goes down onto the top and does other things, right? So topologically, these are slightly different, as in one of them has to be 2 clean sheets, whereas the other one can kind of interweave because we just want it to be rectangles. So that's why it may not apply, and we're not quite sure if it applies yet. As in, we currently are looking at the theorem, or it would be an interesting thing to look at. But anyways, this is all that I have planned for this entire thing. And I want to say a huge thank you for anyone who has come today. And I know it's a long talk, so thank you sincerely.
I can,
And have a
Thank
good
you.
day.
finally go to sleep now.
Yes.
We didn't hold you here. You could have done that earlier. This is on you. Thank you for the talk. That was awesome. I really appreciate it.
I will of course be taking any questions, like technical or non-technical, like whatever, in case anyone has any.
I don't think anyone has questions.
I mean, Sawdust is typing, so I would like presumably I would wait. Yeah. Yes. But yeah. Everything is important. Okay. This is the end of my talk, and I will see you next time. Even though I have no idea what I'm gonna do next time, and it's.
I might do a talk. I mean,
I mean,
someday.